So continuing with our next lecture, we will see what are the engineering applications of FEM. So basically, this finite element method, that is FEM, was developed for the analysis of aircraft structures. Later, it began for the application of general problems in engineering. Wide variety of applications in engineering are used for solving FEM. So these are some of the following analysis in which the FEM is used. In structural analysis, to find the deformations, stresses, strains, and reactions forces in a structure. Structural applications, to find the displacement, stresses, strains, and the reactions in a particular structure. In thermal field, to find the temperature distribution in an object, that is heat lost or heat gained, thermal gradients, and heat flux. In fluid flow problems, to find the velocity, pressure distributions, temperatures in the fluid. Electrical and electrostatics, solenoid actuators, motors, transformers, etc. So these are used in the following industries, that is aerospace and automotive industries, biomedical industries, bridges and building, that is structural, electronics and semiconductors, manufacturing. So these are some of the industries which use this FEM method for solving their problem. So we can see here some of the engineering applications of FEM in different fields. Various softwares are employed nowadays by FEM softwares to find out the displacement, stresses, strains, heat flux, temperature. You can see here many applications. So we will have a look at what are the advantages of FEM. What are the advantages of FEM over the other techniques like experimental techniques and theoretical approaches? Just have a look here. First one is model irregular shaped bodies quite easily. So as I told in the first introduction itself, irregular shaped bodies can be modeled easily without any problems. Handle different load conditions without difficulty. Different types of loading and boundary conditions can be handled. When there are many loading conditions in a problem, like loading at different places, different types of loading, and different boundary conditions, at this point of time, this FEM method is quite useful in comparison with other problem solving techniques. Model body is composed of several different materials. So nowadays many composite materials are used as application in many of the industries or sectors. So this composite materials also can be modeled by this FEM method, which is not possible or it may be difficult to do in other type of problem solving approach. So this FEM method makes the modeling of bodies composed of several materials easier when in comparison with other techniques. Handle different kinds of boundary conditions. So even this is one of the very major advantage. Different kinds of boundary conditions can be handled easily without any problem. Vary the size of elements to make it possible to use small elements wherever necessary. So as I explained previously, so basically this finite element method means dividing a structure into small parts called as elements. So it can be divided into the n number of parts. So one more thing is even we can vary the size of the elements, large elements, small elements. Okay. So by varying the small size of the elements, we can refine the results. So this is one of the major advantage that varying the size of the element makes it possible to use small elements wherever necessary. Alter the finite element model relatively easily. So if any modifications are required, if any changes are required, if any revisions has to be made, so the alterations can be made quite easily without any much difficulty or without any uh, much wastage of time and money. Any small alteration, any other kind of alterations can be made quite easily. Include dynamic effects. Even dynamic effects can be uh, studied under this finite element method. Not only static, even the dynamic type of loading conditions can be studied. We can see some of the applications of FEM, wherein a connecting rod and a plate is modeled and boundary conditions are applied, loading and boundary conditions are applied, and analysis is carried out. Steps involved in FEM. So what are all the steps that are involved in this finite element method? The solution of general continuum problem by finite element method always follows an orderly step-by-step process. The step-by-step process with reference to static structural problems can be stated as follows. Okay. So keeping static structural problem as a reference. So these are the steps that are followed in finite element method. First one is discretization of structure, means we will be dividing the given structure into elements. See. The first step of the finite element method is to divide the given continuum or structure into subregions called elements. Hence, the structure is to be modeled with suitable finite elements. The number, type, size, and arrangement of the elements are to be decided based on the accuracy required. Size of the accuracy required. Next is selection of proper interpolation or displacement model. We have to select a suitable interpolation model or interpolation polynomial or displacement model or displacement polynomial. The displacement solution of a structure or a continuum under any specific load conditions cannot be predicted exactly. It is an unknown parameter. We assume suitable solution within an element to approximate the unknown solution. So in this step we assume an approximate solution. Instead of getting an exact solution, we get an approximate solution. So we assume an proper interpolation model depending upon the type of the element we have chosen. The assumed solution is known as displacement model. In general, a polynomial form of solution and displacement model is assumed. So we take a polynomial form of an equation for this displacement model to be assumed. Derivation of elemental stiffness matrix and load vectors. Next up is from the assumed displacement model, what we do is we derive stiffness matrix K and the load vector F for an element which has to be derived. So this is given in the problem wherein we'll be knowing the loading conditions. So keeping this in mind and taking the assumed displacement model into consideration, first we form the elemental stiffness matrix and then we form the load vector by taking the given loads into consideration. Assemblage of elemental equations to obtain overall equilibrium equations. Next, what we do is we assemble all these elemental stiffness matrix. Since the structure is composed of several finite elements, the individual elemental stiffness matrix and load vectors are to be assembled in a suitable manner and the overall equilibrium equations has to be formulated as K into Q is equal to F. This is the equilibrium equation where K is the stiffness matrix, Q is the displacement and F is the force. K is the global stiffness matrix, Q is the global nodal displacement vector and F is the global nodal forces vector for a complete structure. Next step is solution for the unknown nodal displacements. So after this we will be solving for unknown nodal displacements. Unknown nodal displacements are found from the equilibrium equations of the structure or continuum after applying the boundary conditions of the problem. So after assembling the elemental stiffness matrix into global stiffness matrix and finding or writing down the displacement vector and the force vector, we will be solving for the unknown displacement. So first step, first unknown is to find the unknown displacements in a structural problem, and then we will be finding out the stresses and strains associated in the problem. Computation of elemental stresses and strains. So after the displacement is found out, we will be finding out the stresses and strains in the structure. From the known nodal displacements, the element strain and stresses are computed by using the necessary equations. Next, the phases in finite element analysis. Reprocessing. So this is the first phase wherein the analyst develops a finite element mesh to divide the given geometry into subdomains for mathematical analysis and applies mathematical properties and boundary conditions. So this is the first step. We will be giving all the input to the problem like the loading condition, boundary condition, material properties and all. So this is the pre-processing stage. We will be giving all the input. Next is the solution stage, during which the program derives the governing matrix equations from the model and solves for the primary quantities. So this is the stage wherein the program derives the matrix equations and it forms the model and solves for the primary quantities. Next is the post-processing stage. So in this post-processing stage, the analyst checks the validity of the solution and examines the values of primary quantities such as displacements and stresses. Post-processor software contains sophisticated routines used for sorting, printing, and plotting selected results from the finite element solution. So this is the last phase wherein we will be verifying or seeing our results by printing, plotting, and in the analyst will be checking the validity of the result. The primary results obtained are the displacements, stresses, and the strains. So these are the three phases in a finite element analysis, that is reprocessing, solution, and the post processing. FEA software packages. So many FEA software packages are used nowadays. So some of the FEA software packages that are used for this finite element analysis are ANSYS, Adina, Abacus, Hypermesh, NX Nastran, Cosmos, NISA, Mark, LS, Dyna. So these are some of the FEA software packages that are used by several industries for this finite element analysis to be carried out. So ANSYS is mostly Most widely used MSC data on events is when software that is used.